In this video, we will study complex numbers and complex exponentials. These will be used quite often solving linear responsive first and second order ODEs. Before we go into these topics, let's briefly review the key properties of complex numbers. The complex number, we usually write it z is equal to a plus bi, and this a part here, this is real part, and this part is imaginary part. And I'm sure that all of you know how to add two complex numbers. For example, z is a plus bi, and w is c plus di, and you know how to add z plus w, right? So you just add real part and add imaginary part, right? Similarly, you can actually get z minus w, right? So I'm sure you can do this one. And how about multiplication? How about z times w? Okay, that is just same as before. I mean, it's similar to just multiplication of two real numbers, except that you need to take care of the i's, right? So if I do it here, a plus bi times c plus di, then what do you get? Find the ones which gives us real. So this guy gives us real, right? So a, c, and this guy also gives us real, right? So bd, but because we have two i's, it becomes minus I, because we know that I squared is equal to minus 1. This is the property of the imaginary number. So ac minus bd, this is real part, and we have imaginary part left, plus I, and imaginary part comes from where? Comes from these guys, right? AD, and with these guys, plus BC, right? So this is how we multiply two complex numbers. And the division here is just nothing but a plus bi divided by c plus di, right? And by multiplying its conjugate in the numerator and denominator, for example here, c minus di over c minus di. I didn't change anything because I multiply just same number here, right? Just this is 1, right? This guy is 1, so I didn't change anything. And then we actually got denominator becomes c squared plus d squared, and numerator becomes what? I think you can actually calculate this numerator, right? That is ac plus, right, bd plus I, and bc minus ad. So this is how you can actually calculate in the sum, subtraction, and the multiplication and division with two complex numbers. Now, as I used before, the conjugate here of z, we write it here is z bar, and if this is a plus bi, this becomes a minus bi, right? So this is the definition of conjugate. And the important thing about complex numbers is that they connect algebra and geometry. So what do I mean by this? Algebra is just the numbers, right, with signs, and geometry is a picture, right? So if you draw, I mean, first write it down here. Algebra, so a plus bi, this is algebra, right? What is geometry? I said it's a picture, right? So the interesting thing is that with this imaginary number, you can draw this guy on the graph. For example, this is complex plane, so the x-axis is real part, y-axis is imaginary part. So if the value of a is here and value of b is here, right, then the complex number z, which is a plus bi, becomes this point. So you can draw a line from the origin to this point, and this point represents z, which is a plus bi. So this is how complex numbers connect algebra and geometry. So let's look at this picture in more detail here. So there's two things which is actually important here. One is the size of this line. So that is actually called modulus of z. So this length r is called modulus of z, or we write it using this notation. And the angle here between this line with the x-axis, rear axis here, right? We call it theta, and we name it as the argument or phase of z. So, and we write it arg of z, right? Using this geometric representation of complex numbers, we can actually derive an important formula. Okay, let's do it here. So z, we know that is equal to a plus bi, right? And we know that the a here, the length here of a, using just sines and cosines, we can write it as what? This is r times what? R times cosine theta, right? That is actually a, right? And plus, what is b? b is r sine theta, right? And we have I here, okay? Then we can write this guy as what? We can write this guy as r cosine theta plus I sine theta, right? And the next line is one of the most important formula here in engineering mathematics, and you need to memorize it here. We can write this guy as r e to the I theta. So this is a definition. You can take it as a definition. Then what? Then you can write e to the I theta is equal to cosine theta plus I sine theta. And this formula is called Euler's formula. Using Euler's method, we can actually simplify many complicated manipulations of complex numbers. For example, the multiplication of two complex numbers, z, w, right? And we just did it with expanding a plus bi times c plus di, right? And we just got it by expanding this expression here. But if we use Euler, we can make this multiplication quite simple. For example, if z can be represented in polar coding, for example, in this picture right here. So in this way, we can write z is r1, which is modulus of z, times e to the I theta 1. This is modulus, argument of z. And w in the same way, we can write it this way, r2 e to the I theta 2, right? Then the multiplication zw is nothing but r1 times r2 e to the I theta 1 plus theta 2, right? That is, you multiply its modulus here and you sum their arguments. This is how you multiply two complex numbers using Euler's formula. Now, let's do some example here. So, this is how we can use Euler to simplify many complicated calculations. Next one is this guy. E to the I theta 1, e to the I theta 2 is actually, what is it? This is e to the I theta 1 plus theta 2, right? So what does it mean? Actually, this represents something interesting. That is, the left hand side, this is cosine theta 1 plus I sine theta 1 times cosine theta 2 plus I sine theta 2, right? It's equal to what? Cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. This is real part, right? And plus imaginary part, I times that comes from this cross thing here, right? Multiplying these two and multiplying these two. So that is cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2, right? Okay, this is left hand side. How about the right hand side? Right hand side is what? Right hand side is simple, right? This guy is just cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. So, what have we achieved here? The thing here is that the formula for this thing, right? Cosine theta 1 plus theta 2, do you remember what it is? This is actually same as this guy, right? Okay, do you remember the formula? Is it same as this guy? I mean, what we are doing here, left hand side should be same as right hand side, right? From this equation, right? And that should be true when the rear part of this right hand side should be same as rear part of the left hand side. How about the imaginary part? Imaginary part on the right hand side should be same as imaginary part on the left hand side. Do you see the formula here? Actually, the sum of two angles here, sine theta 1 plus theta 2, can be given in this way, right? So this is how Euler's formula can actually make the calculation quite simple. And let's look at the next example. Here, let's extend what we had before. So, for example, we have e to the I theta cubed is what? This is same as e to the 3I theta. Why? Because you know that e to the 3a here is what? This is e to the a, e to the a, e to the a, right? This is e to the a cubed, right? So we have this guy, and we can actually extend it, right? So this is what? The left hand side is equal to cosine theta plus I sine theta cubed, right? And you can extend it, right? Expand it. And the right hand side, if you move it here, this is what? This is cosine 3 theta plus I sine 3 theta. So what do you say? So the rear part on the right hand side should be same as the rear part on the left hand side after expanding, right? So same way you can actually get the formula for sine 3 theta, right? This is actually imaginary part of this expansion. So this is how you can actually get the formula for cosine theta and sine 3 theta. And next example is about differentiation. So we know that if we differentiate dt e to the at, what do you get? You get a e to the at, right? How about if we have complex functions? For example, differentiate the theta e to the I theta. The question here is the same as I e to the I theta. To find it out, we can actually apply Euler's formula here. So the left hand side here is this d theta. E to the I theta is what? Using Euler, it becomes cosine theta plus I sine theta. And we know that this is what? This is minus sine theta plus I cosine theta. Okay? And this is what? This is I cosine theta plus I sine theta. Right? And again, using Euler, this becomes I e to the I theta. So, using Euler's formula, we show that this is actually true. This is right hand side. Okay? So in the next video, we will use these things to actually calculate the response of the first order ODEs.